Hello, we are Alejandro Gonzalez, Wei Cheng Hisen, and Fabrizio Fuentes, and we're going to talk about the impact of climate change in water resources. Before we begin, there are some things you need to know. The confidence scale. It shows the relationship of agreement and evidence and their relation to confidence. Basically, if you have robust evidence and there's high agreement with it, the confidence we should put on it is high, and the other way around. If the evidence is low and if there is low agreement, the confidence we should put on it is low. Now that you know what the confidence scale is, we can start. Water resources. Water is a locally variable resource, and its availability as well as vulnerability to water-related hazards differ between regions. Anthropogenic climate change is one of many stressors of water resources, but non-climatic drivers also challenge the sustainability of resources by decreasing water supply or increasing demand. The key points with high or very high confidence from the IPCC reports are the observed and projected impacts of climate change on freshwater systems and their management are due mainly to increases in temperature and sea level, local changes of precipitation, and changes in the variability of those quantities. Semi-arid and arid regions are particularly exposed. Reduction of water quality is mainly due to warmer water, more intense precipitation, and longer periods of low flow, and that has impacts on ecosystems, human health, and reliability on operating costs of water services. Climate change affects water management infrastructure and practice. Adaptation and risk management practices have been developed for the water sector in some countries and regions. The negative impacts of climate change on freshwater systems outweigh its benefits. Observe hydrological changes due to climate change. As I said before, a documented hydrological change is not necessarily due to anthropogenic climate change. For robust attribution to climate change, all the drivers of the hydrological change must be identified, meaning that this is usually difficult. Nonetheless, many hydrological impacts can be attributed confidently to their climatic drivers. According to regional observations, most droughts and extreme rainfall events of the 90s and 2000s have been the worst since the 50s. Most regional changes in precipitation are attributed either to internal variability of the atmospheric circulation or to global warming. It was estimated that anthropogenic forcing in the 20th century contributed significantly to observed changes in global and regional precipitation. Changes in snowfall amounts are intermediate, however, consistent with observed warming, shorter snowfall seasons, and with the snowmelt seasons starting earlier over most of the northern hemisphere. Steady decreases since the 60s of global and regional evapotranspiration have been attributed to changes in precipitation, diurnal temperature range, aerosol concentration, solar radiation, vapor pressure deficit, and wind speed. Attribution of observed changes in groundwater level, storage, or discharge to climatic changes is difficult. Observed trends are largely attributable to land use changes and groundwater abstractions. Most observed changes of water quality due to climate change are known from isolated studies. mostly of rivers or lakes in high-income countries of a small number of variables. Take as an example the orange point with the number 13 in this graph. The 13 means the situation, the observed change. 13 is increased anoxia in a reservoir, moderated during El Niño Southern Oscillation episodes in Spain during 1964 to 1991 and 1994 to 2007. It has medium to high degree of confidence in the attribution, which is decreased runoff due to decreased precipitation and increased evaporative demand, and high degree of confidence in its detection. Precipitation extremes in many regions have increased since 1950, which suggests an increase in rainfall erosivity that would enhance soil erosion and sediment loads, but the effects of climate change on these are frequently obscured by human agricultural management and activities. There is low confidence due to limited evidence that anthropogenic climate change has affected the frequency and magnitude of floods at a global scale. Drivers of change for freshwater resources. Precipitation and potential evaporation are the main climatic drivers controlling freshwater resources. Temperature has increased in recent decades while surface and tropospheric relative humidity have changed little. Among other climatic drivers are atmospheric CO2, which affects plant transpiration, and deposited black carbon and dust, both of which enhance the melting of snow and ice by reducing the surface albedo even in very small concentrations. There exists uncertainty in the climatic drivers mainly due to internal variability of the atmospheric system and inaccurate modeling of the atmospheric response to external forcing. In addition to climatic impacts, the future of freshwater systems will be impacted strongly by demographic, socioeconomic, and technical changes, including lifestyle change, but they are non-climatic factors. Projected hydrological changes. Based on global and regional climate models, potential evapotranspiration over most land areas is very likely to increase in a warmer climate, thereby accelerating the hydrological cycle. All projections for the 21st century show continued mass loss from glaciers. As the glaciers shrink, the relative contribution decreases and the annual runoff peak shifts towards spring. This shift is expected with very high confidence in most regions. If they're in equilibrium, glaciers reduce the interannual variability of water resources by storing water during cold or wet years and releasing it during warm years. As glaciers shrink, their diminishing influence may make the water supplies less dependable. Climate change affects the quality of water through a completely set of natural and anthropogenic mechanisms working in parallel and in series. Projections under climate change scenarios are difficult. In consequence, there are few projections of the impacts of climate change on water quality where available. Their uncertainty is high. Heavy rainfalls are likely to become more intense and frequent during the 21st century in many parts of the world, which may lead to more intense soil erosion even if the total rainfall does not increase. The largest increases are expected in semi-arid areas. Climate change will also affect the sediment load in rivers by altering water discharge and land cover. Increases in total precipitation, increased runoff, and from glaciers, and the shift of precipitation from snow to rain will further increase soil erosion and sediment loads in colder regions. Climate change is projected to alter the frequency and magnitude of both floods and droughts. The impact is expected to vary from region to region. The few available studies suggest that flood hazards will increase over more than half of the globe, but decreases are projected in parts of northern and eastern Europe, central and East Asia, central North America, and southern South America. Limited evidence, but high agreement. Worldwide, the damage from floods will increase because more people and more assets will be in harm's way. By the end of the 21st century, meteorological droughts, less rainfall, and agricultural droughts, drier soil, are projected to become longer or more frequent or both in some regions and some seasons because of reduced rainfall and or increased evaporation or both. In dry regions, more intense droughts will stress water supply systems. In water regions, more intense seasonal droughts can be managed by current water supply systems and by adaptation. Projected impacts, vulnerabilities, and risks. When talking about availability of water resources, about 80% of the world's population already suffers serious threats to its water security, as measured by indicators including water availability, water demand, and pollution. Climate change can alter the availability of water, therefore threaten water security according to UNESCO. Reliable surface water supply is expected to decrease due to increased variability of river flow, that is due in turn to increased precipitation variability and decreased snow and ice storage. Water uses. When talking about water uses in agriculture, there is high confidence that irrigation demand will increase significantly in many areas. Rain-fed agriculture is vulnerable to increasing precipitation variability. When talking about energy production, climate change affects hydropower generation through changes in the mean annual stream flow, shifts of seasonal flow, and increases of stream flow variability, as well as by increased evaporation from reservoirs and changes in sediment fluxes. Therefore, the impact of climate change on a specific hydropower plant will depend on the local change of these characteristics. When talking about municipal services, water utilities are confronted by higher ambient temperatures, which reduces snow and ice volumes and increase the evaporation rate from lakes, reservoirs, and aquifers. These changes decrease natural storage of water and hence, unless precipitation increases, its availability. Moreover, higher ambient temperatures increase water demand. Shifts in timing of river flows and possible more frequent or intense droughts, which increase the need for artificial water storage. Higher water temperatures, which encourage algal blooms and increase risks from cyanotoxins and natural organic matter in water sources, requiring additional or new treatment of drinking water. High agreement with medium evidences. Possibly drier conditions which increase pollutant concentrations, and increase storm runoffs which increases loads of pathogens, nutrients, and suspended sediment. Also sea level rise, which increases the salinity of coastal aquifers, in particular where groundwater recharge is also expected to decrease. Climate change also impacts water quality indirectly. More frequent and severe forest wildfire could seriously degrade water quality. Many drinking water plants, specifically small ones, are not designed to handle the more extreme influent variations that are to be expected under climate change. See, sanitation technologies vary in their resilience to climate change impacts. For sewage, three climatic conditions are of interest: wet weather, which includes heavy rains, mean increased amounts of water, and wastewater in combined systems for short periods. Dry weather, which means soil shrinks, which would make the soil shrink as it dries, causing water mains and sewers to crack, making them vulnerable to infiltration and exfiltration of water and wastewater. And the sea level rise, which which would contain the intrusion of salty water into sewers, necessitates requires processes that can handle saltier wastewater. When talking about freshwater ecosystems, freshwater ecosystems are affected through increased water temperatures, altered stream flow regimes, river water levels, and extent and timing of inundation. They are also affected by water quality changes induced by climate change. I'm talking about other uses. Indirect impacts of hydrological changes are expected for navigation, transportation, tourism, and urban planning. Social and political problems can result from hydrological changes. Adaptation and managing risks. Options. Climate change provides many opportunities for low regrets solutions capable of yielding social and/or economic benefits and adapted both to variability and to change. The next table shows some categories of climate change adaptation options for the management of water resources. For example, we have the category of institutional, and we have some options. For example, build adaptive capacity. That's an option. Or another would be increase resilience by forming water utility network working teams. And there are many more in design and operation. Carry out programs to protect water resources in quantity and quality. There are many options that shows different ways of adapting. These are some low regret. When dealing with uncertainty in future climate change, it should be represented differently because it would be impossible. There is no correct way to take uncertainty into consideration when talking about water adaptation to water resources and to the impacts of climate change on water resources. Also, calculating the global cost of adaptation in the water sector is a difficult task, an extremely difficult task, and results are highly uncertain. Adaptation in other sectors such as agriculture, forestry, and industry might have impacts on freshwater systems, and therefore needs to be reconsidered while planning adaptation in the water sector. Conclusions. Many factors make studies on freshwater resources extremely difficult. There is no possible way to predict exactly what would happen because of the high amount of uncertainty, the high amount of variables that climate throws at us. However, we can start to make some progress progress towards adaptation and mitigation, just like the table with options showed. But not only those, also by treating more carefully water and not wasting it. The small actions we do. In some countries, they've already started to take some action. Mostly in rich countries, but they have started to implementing those adaptation and mitigation plans to start and act. Thank you.